Hi, this is Teams 2 Engineering Design 1 project, and th- our project is called the Smart Home Gym, an interactive workout system. The team members in this project will be Juan Perez, Laura Goaz, Leo Herrera, Alexandra Zulga, and Mulga. So the problem that we're trying to address with this project is this. Obesity is a serious concern because it's often associated with poorer mental health, reduced quality of life, and is often associated with the leading cause of death in the United States, such as diabetes, heart disease, stroke, and other types of cancers. It results from a combination of causes such as lack of physical activity, dietary patterns, medication use, and genetics. Additionally, even if a person does decide to be more active or want to be more active, life can get in the way, such as classes, work, or other activities. Gym membership, personal trainers, and workout equipment can be pricey, and even if a person can afford this, they tend to take up a lot of space in their homes, which makes it hard to use. During the COVID-19 pandemic, with closed gyms and social distancing policies, many people have decided to start exercising at home. However, many people do not have the necessary knowledge to establish a good routine or maintain an appropriate technique and avoid injuries.
As a solution, we created the Smart Home Gym. The Smart Home Gym will benefit users of all ages by providing remote workout resources to aid individuals with trouble working out at home. This is an innovation that provides users with the opportunity and support to include fitness into their lives.
This product will be more private and less expensive than going to a gym normally would. Also, it is a standalone product made to contest similar products in the field as a cheaper alternative. The smart home gym can be used by people of different ages. We aim to attract adolescent users and adult users so that as a community, everyone can work on providing yourself with a fun and healthy solution to being out of shape. This product will also benefit personal fitness trainers that are left jobless during moments of social distancing. In this image, we can see the system overview.
Front-end design and development. Components. Electron will be our first application that we're going to use on Smart Mirror. It's a framework for creating native applications with the web technologies like JavaScript, HTML, and CSS. It takes care of the hard parts so we can focus on the core of our application for the Smart Gym system. It also has the facility of auto-updating and crash reporting on the Windows and Mac. The crash reports are submitted to remote server for the further analysis. The Flutter is an app SDK for building high-performance, high-fidelity apps for the iOS, Android, web, and the desktop from a single code base. The goal is to enable developers to deliver high-performance apps that feel natural on different platforms. This app will be work on iOS and Android. Flutter apps are written in the Dart and C++ language and make use of many of the language's more advanced features. Electron also use C++ and Python languages besides than JavaScript, HTML, and CSS. Why they are needed? The system UI will be made by Node.js, which uses CSS, HTML, and JavaScript. It should be uncluttered and mostly focus on important figures such as videos, video calls with other people, and showing your progress over the time. The app will be run by using the latest version of Electron and desktop cross-platform framework which is based on Node.js. The mobile app will have most of the information and it is made using Flutter which has its own interface to design the UI. The app will contain the selections of workouts, other people profiles, your workout progress over the time, and the starting video calls with the other people. For the app, controlling the mirror, it will be made using the latest version of Flutter. a mobile cross-platform framework. Interfaces the other components. The Electron class platform will be communicate with the all component such as sensors which is connected to the Raspberry Pi. Raspberry Pi is our microcontroller and it will be responsible for gathering data from the microphone, touchpad, heart rate sensor, interactive mat sensors, and it will be controlled either with the phone app or touchpad. Electron and Flutter app will be communicating and run based on the VPS server and it is database. The VPS server is the Amazon Web Service server which has providing database for the people. Mobile app with Flutter will be remote feature which give us opportunity to user to remote the mirror. Challenges. Every project has some challenges and or we have also some couple challenges here for the front end development. Those challenges are the first one, the app and mirror will be only communicating separately, such as whenever the user opens the video or starts a video call from their smartphone. They will be communicating by either Bluetooth or sockets. We have a second challenges here. The user will be simply use their phone to select their favorite workout, and after doing the workout will play on the screen and sequences of the steps for the workout will be displayed on the mat. These all challenges will be on Electron. Also, we have some challenges for the mobile app, which we were going to use AI services on that information will be accessed by the phone for mobile app. This is our third challenge, and there's also last challenge we have right now is communicate between mobile app and Raspberry Pi. Our early prototype is going to have UI and UX designs for the Flutter and Electron application published and developed. There is another feature of remote control for the Electron app will be also enabled, so we can use our iOS and Android mobile application to remote the system. There's camera and other components will be connected to Raspberry Pi and we can manage them on Electron application. There is some AI features added and there is perfect feature of face-to-face calling also enabled and our trainers and students or users will call each other with this system.
Hi, so I'm Leo Herrera, and I'll be doing the servers and backend. There are three components to the servers and backend that we'll be using. There are all AWS related. There will be AWS EC2, which is Amazon Elastic Compute Cloud. That is basically an infrastructure as a service that basically provide us with a virtual machine that we could run whatever we need on as a server. The next component will be AWS S3, which is Simple Storage Service. It's an object storage service, which means we can save things such as files, videos, or any other stuff. We'll be mostly using them for videos that the user records, that users and trainers record. The last component will be AWS RDS. So that's Relational Database Service, which is basically just hosting a database on AWS to make to make management of it easy, and we could just focus on worrying on getting the databases up. So the reason why we need all components, I'll break it down. And I'll break it down now. So AWS EC2 is needed because we need to have a turn/stun server. That server is used in the WebRTC protocol to establish a connection to the user we want to talk to. So for video calls or for group video calls, all, every user will need to communicate with this server to establish a connection between everybody who's calling and then proceed with the call. So this EC2 must be used for that purpose, as well as if we need a REST API in front of the databases, because for some reason we may not be able to pull the databases directly from either Node.js or from Flutter, then we would have to have a workaround and use a REST server to be able to call the information on there. The S3 is needed for video storage because it is the simplest way of saving and retrieving videos that the trainers or users record. And then RWS the will be hosting the databases, such if we're going to end up using MySQL. If we end up using MongoDB instead, we will be using EC2. So some of the challenges with the server will be these. As users are able to record and upload videos in high quality, we need to make sure that we don't use too much memory in the S3 servers, as we will need to pay for that. Some of the solutions that I've thought of for these challenges would be to using a compression algorithm to make the videos smaller when we upload them and then decompressing them before showing the user. But we need to look into it more before we finalize what we will do. Another challenge will be choosing between MySQL or MongoDB for the database. Both have their benefits and drawbacks, and we need to decide before we start creating these servers, as they will be hosted in different places. The last challenge will be a REST server may be necessary for the databases, depending on the package support on Flutter or Node.js. If it's not supported, and it would be a complicated way to call in the servers, we will just add a API, a REST HTTP API, and then we'll get the information back in a JSON format that will be simple and easy to understand, and would avoid the problem of having to call the server in a complicated manner. All right, so for the early prototype, what we are imagining to see is the users and videos databases up and running, meaning all the user information, such as their progress, their personal information, and stuff like that will be in the user databases, and the video metadata, such as where it's located in S3, what type of exercises, anything related to the AI would all be in the video metadata. The next example would be sample videos in the object storage, obviously, because we would need those for the video databases as well. And then, last but not least, video calling up and running between two users using the turn/stun server hosted on AWS.
Hello, my name is Alexandra, and I will be talking about the artificial intelligence in our project. Our main component, our mat, will be a smart mat because it will be an integrated pressure sensing model where it could distinguish when the user is on the mat in certain positions. So I'll begin with our first major step is fabricating the sensors that we chose for our mat with electrical conducting fabric. We chose these sensors because they can easily be fabricated for covering large areas while relying on a low-cost process. So for our deep learning, we will be using a KNN classifier, nearest neighbors, to distinguish about 5 to 10 exercises. We will be aiming for an accuracy rate of at least 75%. One thing to know is that we will need to pre-process the data frames. That's image restoration. And it'll be necessary in order to cut down on any noise in the contact area. So we can do this by applying a filter. And the image restoration will enhance the image quality because it tends to be blurred due to noise of the environmental factors. So it could really lower down the quality of the image if we don't have a filter to filter out everything else. So we can apply a reusable filter for degradation here. For this model, we will be using the infamous Wiener filter. The Wiener filter gives maximum peak signal noise ratio, PSNR value, and minimum mean squared error value. So when comparing other techniques of image restoration, the Wiener filter was found to be the best applied for our system. For time's sake, and optimal amount of training rounds, data can manually be programmed to an 8-bit solution So it'll allow processing and storing each pixel in our sensor matrix to be cut to a more speedy process. Data imaging and sensor calibration will be logistically programmed onto the microcontroller firmware using our created environment. The completion of the sensing mat will immediately be followed by the creation of our testing dataset. We will record the inputs received from the mat when used by various different users, at least 5. And these inputs and their associated label will also be used in the training data. So it'll have a label for push-up or planking, sit-ups, or standing exercises. So basically our smart mat will be able to distinguish whole body parts when they're being pressed onto the mat, such as hands, feet, forearms, knees, and your entire back. So we designed a decision tree to show how our AI system will be able to identify when the user is performing a certain exercise. The light gray shapes here represent the decisions being tested and verified when the user becomes in physical contact on the smart mat. Our AI system will be using a number of individual pressured areas on the mat and the size of the area being pressured on the mat as thresholds. Before saying anything else, I just want to mention that thresholds on the yellow sticky notes are there for helping to paint a picture of how our system will identify these types of exercise positions. These thresholds are very likely to change during our training process with our smart mat. So, when the workout system is on and the user initiates smart mode, the mat will wait for the user to step on the mat. When the pressure at this point surpasses about 30 pounds, then the first node outputs yes, and we reach the 2 feet decision node. At this stage, if we detect pressure at 2 different points on the mat, then the decision node will output a yes. One note is that we will also make sure that items that are not identified as human body parts will not be included in the testing data here. Moreover, if the system detects 2 feet, then the system will initiate standing mode, and the smart camera will turn on from the display and detect upper body reps or jumping reps with either image processing or motion detection. With every rep, the system will keep track of the amount of reps and the exact start-end times. The system will also notify the user when they have completed all the required reps and gives them a customizable amount of time before starting next set of reps. A safety precaution I noted here is that we will ensure that permission must be granted in order to turn on the camera each time. Moving on to the planking position, the decision node will be, for this one, will be a little bit more difficult to position because we will use the number of areas, and if the area is at least 3, so 3 different areas being pressured, then the system will identify the symmetry of the pressure points to be planking position. Thus, the user will be able to have a start and end timer activated as soon as the plank position becomes an action. This will also work for push-ups or any positions with your palms on the mat. Moving on to the laying down exercises, the system will be looking for the detection of one large pressure area with a threshold of, my guess, is about 20 inches. When the mat detects a large area of pressure, then the image will be sent to laying down exercise dataset for testing. So we'll have 3 different datasets, one for standing mode, or 2 feet, one for planking, and one for laying down. This is a diagram of our epics and our incremental approach towards getting out our major features and components on time.
Hi, my name is Juan Perez. I'm an electrical engineering student, and today I'm going to be talking about one of the components of the smart home gym, which is the smart workout mat. So I'm going to begin with the workout mat design. The workout mat will be designed to indicate where the user should position their feet, and it will also sense when they have stepped into the right position. This would make the workout fun and easy to follow, and in addition, it will track the user's performance. The mat will be approximately 16 square feet, which would allow the user to make big jumps during the workout. The mat will contain LED lights and 16 pressure sensors. So here we can see a few of the workout mat parts. We will include a high impact workout mat. We're going to need a Raspberry Pi. We're also going to need LED strips, 16 individual pressure sensors, and a power supply. So we'll be implementing a high impact foam mat. And this high impact foam mat will provide the user with a safe surface to work on, and it will also offer protection from damage to the pressure sensor, which will be placed under the mat. Okay, so we plan on using some LED strips for this project, and we plan on using the WS2812B LED strips. This LED strip allows us to individually control each one of the LEDs to change the color and speed independently of the other LEDs. By configuring them in zigzag, we'll be able to individually address each LED using only one PWM port from the Raspberry Pi. We plan on using Python to program the LEDs to perform the steps of each workout, and the foam mat will have to be modified so we can insert the LED strips with a protecting see-through plastic in case the user accidentally steps on them. We'll also be implementing pressure sensors to our design. And after doing research on the pressure sensors, we discovered that they can be very expensive. Because the mat will need 16 different sensors with approximately 1 square foot each, we decided we would have to build our own to cut costs. We plan on using a pressure-sensitive resistive sheet called Velostat and a ripstop silver conductive fabric. Think of the sensor as a sandwich. The Velostat sheet will be placed in the middle of two conductive fabric sheets. Voltage and ground will be applied to these conductive fabric sheets respectively. When pressure is applied to the Velostat sheet, its resistance decreases, thus completing the circuit. Using this information, we'll be able to determine when the user initially steps on the mat, when the user has stepped in the correct position, and indicate where the next step will be. Before choosing the ripstop fabric, we considered the advantages and disadvantages against other types of fabrics such as the nickel copper ripstop fabric and the copper polyester fabric, which are also good options but could cause skin irritations to the user. The ripstop fabric is gentle to the skin and offers a resistivity of less than 0.25 ohms per square foot. Additionally, since this fabric is washable, in the event the user spills liquid on top of the mat, there won't be any issues. However, we also intend to cover our sensors with impermeable fabric to further protect them. So here are some of the mat uses. With this mat, the user will be able to perform a variety of home exercises such as high knees, lunges, squat jumps, frog leaps, push-ups, planks, yoga, and many other exercises. And here I'm going to talk about how it works. After the user selects the workout, the LEDs will light up to indicate where the user should step into. After the user steps into the position, using the pressure sensor, we will confirm that the user stepped into the indicated position, and then the next step will be displayed. By keeping track of how fast the user is moving through the workout, we'll be able to measure the performance of the workout to provide helpful feedback. In the image to the right, we can see the red LEDs are indicating where the user stepped on, and the green LEDs indicate where the next step is. Okay, and these are some of the challenges we identified. And one of them is correctly biasing the voltage level of the pressure sensor in a way that is safe for the user, but that also reads correctly when the user has stepped on the mat and not generate random readings. The other one is correctly coding the LEDs, so the user will know where the next step will be, and simultaneously give feedback to the user of where the user has already stepped on.
Hi, my name is Laura Goes, and I'm now presenting the Smart Mirror display. The Smart Mirror display will be configured to interact with the Raspberry Pi and the software components of this project to provide a visual output to the user. The Smart Mirror will also be equipped with a built-in camera and a microphone. This will allow us to record the workout for useful feedback, and it will also allow for communication with the trainer and other users as well. The user will also be able to take pictures which can be displayed later to show progress. Because we typically see ourselves in the mirror every day, we cannot see the progress that's happening over time. If the user is able to go through a series of photos from a longer time period, they will be able to recognize the progress being done, and it could potentially motivate the user to continue using our product. To be able to build the smart mirror display, we will need to get a monitor, a camera, a microphone, a Raspberry Pi, glass, reflective film, wood frame, and a PIR sensor. Monitor with glass and reflective film. After the user selects the workout, a video with a trainer performing the workout will be played to guide the user through the workout. Because of the reflective film placed in front of the glass, the user will also be able to see themselves performing the workout at the same time. Seeing yourself performing a workout can greatly reduce injuries since the user will be able to identify if they are using proper form for a specific exercise. Camera and microphone. For our project, we intend to use the RASP Cam2, which can be connected to the Raspberry Pi. This camera offers a resolution of 8 megapixels and video of 1080p at 30 frames per second or 720p at 60 frames per second. PIR sensor, also known as a passive infrared sensor, will be utilized to offer a low power mode feature to the smart mirror display. When the user walks by the mirror, the PIR sensor will detect movement and turn on the display. How it works. The smart mirror display will have different modes. When the user is not performing a workout, different general information such as time, date, reminders, and weather can be displayed. Using a PIR sensor, we will also be able to implement a low power mode where we turn off the monitor display when no movement is being detected. The user will be able to select the workout using a smartphone app. When the user makes the selection, the app will communicate with the microprocessor to perform the user request. Challenges. Two main challenges were identified for this part of the building process. The first challenge is to select an appropriate power supply capable of safely powering all of the components simultaneously. Our second challenge is building the frame correctly so it looks good aesthetically and capable of safely holding the components in place.
This is our schedule and our milestones listed. We will divide our work into software and hardware generally, and divide the schedule in milestones. I noted ST for software team and HT for hardware team, and the others for everyone. And also noting that both teams are responsible for the entire project, and if any component fails, it falls under the responsibility of the entire group. And these teams do not mean we are solely responsible for attending certain weekly conferences. Each member must attend all conferences in order to remain up to date to all processes and changes being made. Yep, and all of these are listed in our Trello backlog.